Okay, let's continue. So, if you recall, this is how we started. We imagined that we have a system that's in contact with a reservoir. So, there is a small system. Well, it's small compared to the reservoir, but it's still huge in terms of the number of particles is much larger than 1. So, we are going to assume that all the time. So, this system is in contact with the reservoir, and I am just going to fast forward, because I have already told you that we have imagined a situation where the system is allowed to exchange energy with the reservoir or the surroundings, but not anything else. So, in other words, its volume and number of particles are fixed. So, when you do that, you can count the number of ways in which you can rearrange the microstates of the system and the reservoir such that the total internal energy of the system is U1. And because we do not really care about U1, because that keeps fluctuating. So, what we have to do is find the total overall number of ways of doing it, and that is the sum over all the U1s, because they are all independent ways of rearranging the microstates. So, now you can ask yourself, like we did earlier, what is the most probable value of U1, and that is found by maximizing this entropy, rather this product, which tells you the number of number of ways in which you can rearrange the microstates of both the system as well as the surroundings. When you do that, you are able to ascertain you are able to convince yourself that there is a physical meaning to the slope of the entropy versus internal energy. It is not merely formally defined as the reciprocal of the absolute temperature. Rather, the physical meaning is that it is the temperature is what equalizes when you allow two systems in thermal contact to approach equilibrium. So, temperature has a very concrete physical meaning, which is exemplified by this relation, and this is something we rigorously derive by looking for the most probable configuration or the most probable energy which accomplishes this. And so, I told you that if you now start allowing for the walls of the container to be flexible, so that it can compress and expand, then naturally because work gets done, so energy also gets exchanged. So, we are compelled to also imagine that not only the volume, but also the energy fluctuates, but then the total energy of the combined system of the reservoir and the system of interest remains fixed, and so does the volume. So, now you can ask the same question about what is the most probable volume of the system and what is the most probable energy of the system. And so, you get two different equilibrium conditions. One is the usual equilibrium condition, which forces us to equate the temperatures, and because the other condition forces us to equate the slope of the entropy versus volume on the reservoir side equal to the system side. Now, the slope of the entropy versus volume according to thermodynamics is the ratio of the pressure and the temperature. So, recall, just notice that we just equated these two because energy gets exchanged and they reach thermal equilibrium. So, temperatures are anyway equal. So, because the ratio of P and T have to be equal and temperatures are already equal, that also implies that the pressures are equal. So, this is where we left off last time. So, now I am going to go ahead and see if I can do this similar thing to what I did. Even this also we did earlier. So, in order to study the overall number of ways in which you can rearrange the system, what you do is you look at the entropy of the reservoir, and then you realize that U is much larger than U1. So, you can do a Taylor series like this, and then recall that this is nothing but the temperature, the common temperature between the system and the reservoir, and then you can write it like this. So, I am going to show you later that it is legitimate to completely ignore the fluctuations around the most probable state. So, what I have done here, I have simply equated U1 to its most probable value. So the question is, what gives me the right to do that, because after all there is a summation there over U1. So the implication is that the contributions from U1 different from the most probable value is overwhelmingly suppressed compared to the most probable value, and that is for systems which are large in size, which we will establish this a little later. But for now, let us assume that this is legitimate, that I am going to it's legitimate on my part to simply replace the summation and drop the summation and replace U1 by its most probable value. So, in which case I end up getting an expression of this sort, and so this e raised to S2 goes outside, because that is the reservoir which I do not care about. So, if I look at only the system, so I end up being able to write something like this. So, the net way of rearranging the microstates, of course, the net way of doing that for the reservoir times the system, because it is in contact with the reservoir, it is no longer e raised to the entropy of the system. So, the influence of the reservoir has to be now taken into account. So, it is taken into account through what is known as the free energy of the system. So, the free energy is defined as the difference between the internal energy minus the temperature times the entropy at its most, when evaluated the most probable value of the energy. So, now of course, the very term free energy implies that it has some physical meaning, and indeed it does. So, the answer, I mean the physical meaning is that free energy is that energy which is available for you to utilize to do work. So, it's something that that's left over after all the entropy exchange, I mean the energy exchanges are done, and then some of that energy gets irretrievably lost in entropy, and whatever remains is basically what you can use to do work. So, free energy therefore is the energy that remains for you to utilize to do work, useful work. So, this is what is known as Helmholtz free energy. So, now I am going to repeat this calculation when I allow the walls of the container to not be rigid. So, in other words, I allow the walls of the container to move around. So, as a result, I told you already that not only the volume can fluctuate, but also because if I allow the walls of the container to move around, work gets done. As a result, the internal energy also fluctuates. So, as a result, I have to take into account both these processes, and when I do that, I can do something similar to what I was doing earlier, namely this is the system. So, rather this is a reservoir, and the reservoir entropy is now a function of U2, and recall that U2 is nothing but the total energy U, which is fixed, minus the energy of the system, which is U1, which fluctuates. So, it also depends on the volume of the reservoir, which is V2, and V2 is the difference between the total volume of the combined system and the reservoir, which is fixed, and the difference between that and the volume of the system, which is V1, which fluctuates. So, now as usual, as it was in the earlier case, we may Taylor expand in powers of U1 and V1, and we end up with this expression, because now the coefficients are nothing but the slopes of the entropy versus energy, which is reciprocal temperature, and the slope of the entropy versus volume, which is pressure by temperature. So, now as usual, we are entitled, or we take the liberty of replacing the energy of the energy and volume. I should have, sorry, there is a volume summation as well. So, the energy and volume of the system by its most probable value, and its most probable values are determined by equating the temperatures on either side of the system and reservoir, and the pressures as well. So, so you have two equations and two unknowns which get fixed, the two unknowns being the most probable energy and most probable volume of the system. So, as usual, as before rather, we will be able to identify this difference, this plus this. So, in other words, this plus this has a special name, and that goes by the name of Gibbs free energy times a minus beta. So, the Gibbs free energy is therefore defined as U plus PV minus Ts. So, remember that Helmholtz free energy, where you only allow energy to get exchanged between system and reservoir, was U minus Ts. Now, because you are also allowing volume to fluctuate, you have an additional term called PV, V1 star, that is the most probable value. So, this is called Gibbs free energy, and this term here has a special name, it is called enthalpy, and it is sometimes denoted by H. So, so in other words, Gibbs free energy is enthalpy minus Ts, just as Helmholtz free energy was internal energy minus Ts. So, here it is enthalpy minus Ts. So, you can imagine that enthalpy is basically, it takes on the role of internal energy when you allow volume to fluctuate. So, it is the counterpart of internal energy when you allow volume to fluctuate, and that is called enthalpy. So, now just as I told you that the Helmholtz free energy, it is called free energy precisely because you can use it to do work. Here too, this is called Gibbs free energy precisely for the same reason. But notice that here when I say work, I mean work other than the work that gets done because of the volume fluctuations. So, that is discounted because that is already taken into account, that is not useful work, that the system kind of tries to adjust itself. So, you can't do much about this. So, you can't extract any further energy and do additional work. So, that is taken away. So, when you take that away, what remains is the energy that you can utilize actually to do work, and that is called Gibbs free energy. So, now, well, that was a nice physical description of free energy and also temperature and pressure. So, I told you what they mean physically in terms of quantities becoming equal on either side under various conditions of equilibrium. So, that is a physical description which is very useful and important. But now, I am going to switch gears and also tell you about a geometrical or a mathematical geometrical description of Helmholtz free energy. So, it is interesting to note that not only does the Helmholtz free energy and therefore also Gibbs free energy have a physical meaning which is easy to follow, but it also has an important geometrical meaning which is also easy to follow. So, in order to understand the geometrical significance of Helmholtz free energy, so imagine there is a plot. Suppose I plot entropy versus internal energy. Of course, I have purposely plotted it as not a straight line, but in fact, you should be wondering why it is not a straight line, because that appears to violate extensivity. So, we are actually purposely considering situations where extensivity is mildly violated, because we are going to not operate in the thermodynamic limit. So, I told you extensivity is mandated only in the thermodynamic limit. So, if I relax that a little bit, then it's the entropy function need not be completely extensive. So, it can only be approximately extensive. So, if you remember that I told you that I claimed without proof that this goes through a maximum, but that is actually a contradiction if you really assume that S1 and S2 are truly extensive. So, if they are truly extensive, then you see these are just linear functions of u1 and v1, and there is no chance that it goes through a maximum. So, a linear function never goes through a maximum, it just keeps increasing or decreasing. So, it never goes through a maximum. So, obviously, already here when I say this, what I have in mind already is I have something in mind, namely that I am eventually going to accommodate deviations from thermodynamic limit which leads to deviations from extensivity. So, that I already had in mind when I made these assertions, because this would never reach a maximum, or the most probable value wouldn't even exist if that were not the case. So, if I strictly assume extensivity, I would never be able to convince you that this product goes through a maximum. So, I have to accommodate non-extensive entropy, and it's not scary. I mean, it sounds scary now, but you'll see that it's not that difficult to incorporate non-extensivity in a systematic way around the basic result, namely the extensive. So, small fluctuations, small deviations around extensivity can be accommodated easily. So, that is what we have in mind here. So, when we plot the entropy function versus internal energy, and we purposely assume it is not extensive. So, it is not a straight line, in other words. So, there is a kind of curve here. So, now you see, you could either choose to describe this curve. So, the traditional way of describing any curve is to just mark out points on the curve. And what are points? Points are just ordered collections of two numbers. One number corresponds to the x axis, and the other is called ordinate and abscissa, for those of you who are familiar with those terms. But otherwise, it is just the x axis and the y axis labels, I mean the components rather. So, by specifying the the x coordinate of that point and the y coordinate of that point and a whole bunch of such points, and you join them all by a smooth curve, and that is how you describe a curve typically, by listing all the points on the curve. But it so happens that there is an alternative way of describing a curve which does not involve listing all the points that lie on the curve. So, the alternative way of doing that is to instead list a whole bunch of straight lines such that a unique curve can be drawn which is tangent to all of them at the same time. So, in other words, so what you do is you draw a whole bunch of straight lines like this, like this, like this, and then you ask yourself which curve is tangent to all these lines. I mean that, of course, at different points. So, they are all tangent to the curve at different points. So, different straight lines are tangent to the same curve at different points, but then the curve itself is unique and a whole bunch of such straight lines. So, it so happens that you can instead of listing all the points that lie on the curve, so the alternative way of thinking about the curve is to list all the possible straight lines, the family of tangents to the curve. So, that's what we are going to do now. So, let us do that mathematically. So, suppose S1 versus U1 is given. Now, just focus on a particular value of U1 called U1 star. So, remember that we have been calling that the most probable value. So, now suppose I draw a straight line tangent to this curve S of u. So, what is the equation of that straight line? It is going to have a slope which corresponds to S dash U1 star, and it also has the value of S U1 star at U1. So, in other words, if u equals u1 star, y u1 star should be equal to s u1, because I mean they should touch, right. I mean the straight line should touch the curve. So, the y coordinates of the curve and the straight line have to be the same at the place where it touches, and the place where it touches is u equals u1 star. But then not only should it touch, it should also touch in a tangential manner. So, in other words, so how does one ensure that the straight line and the curve touch in a tangential manner? The way you ensure that is by equating the slope of the straight line with the slope of the curve, and which is why I have written it in this manner, and that this way of doing it accomplishes that. So, now that I have got a straight line, notice that this straight line is unique. The moment I pin down what is u1 star and the nature of the function s of u, this straight line becomes unique. Now, because it is unique, I can ask myself what is the value of the y intercept. So, in other words, if u is 0, So what is the value of y? So that is precisely what is known as Helmholtz free energy. So that's the geometrical meaning of Helmholtz free energy. It's the y-intercept. So of course there's a minus beta there, but other than that it's proportional to Helmholtz free energy. So Helmholtz free energy is proportional to the y-intercept of the tangent to the entropy versus energy curve. Okay. So that's the geometrical meaning of Helmholtz free energy. You can see this happening, for example, by this animation that I just created. So this is the family of tangents. So you see that at each point on the curve, I can draw one tangent, another tangent, another tangent, another. So the collection of all those tangents is specifying a collection of all those tangents is the same as specifying points on the curve. So you notice that in order to specify a straight line, which is basically what a tangent is, you need two numbers. One is the slope and the other is the y-intercept. So you have learned that probably in your primary school already. So by specifying the slope and the y-intercept, uniquely pin down a straight line. But what is the physical meaning of the slope here? So the slope is just the inverse temperature, and now the y-intercept, I have just given you a new interpretation, and that is minus beta times Helmholtz free energy. So what you are doing in essence is specifying a straight line by a pair of numbers. So the first entry in that pair is the inverse temperature, the second entry is Helmholtz free energy divided by minus T, which is temperature with a negative sign. So by providing these two numbers, it's the equivalent of providing, so that's an alternative rather to providing u and su. So in other words, you don't have to provide points that lie on the curve, you can alternatively provide the details about the tangent to the curve. So this way of thinking about curves, so in physics the S versus U curve is called a microcanonical description of the system. Canonical, I already told you what it means. It means canon means some rule book. So microcanonical because it kind of talks about combinatorics and counting and that sort of thing. So it's very microscopic. So it's called microcanonical. So the tangent way of doing things, so describing that curve alternatively as a tangent rather than a collection of points, is called the canonical description. So that's the physics terminology. Mathematics people call this transformation between thinking of the curve as a collection of points versus thinking of the curve as a collection of tangents. So that's called, in mathematics language, it's called a Legendre transformation. Okay, so that has a name. So the free energy is sometimes called a Legendre transform of the entropy function. So that's so much for the geometrical description of Helmholtz free energy. So similarly also for Gibbs free energy. So let's get to the important thing which we have kind of glossed over, which is something I told you already. So I told you that I kind of pretended that for instance this goes through a maximum as a function of u1, and I didn't actually prove it, and that seems quite untenable if you assume extensivity. So I already told you if this is proportional to u1, this is proportional to u minus u1, which is u2. There's no chance that this whole thing goes through a maximum because it's linear in u1. So obviously there's something missing, and what is missing is what is referred to as fluctuations, and that's something we'll have to get into right now. Okay, so what does that mean? So the idea is that we of course don't stop here. So what we do is we do a Taylor series around u1 star. So remember that u1 star is the most probable value of the internal energy of the system. So, what I do is that I expand in powers of u1 minus u1 star. So, that is my small quantity. So, I am close to the most probable value of the internal energy. So, I go ahead and expand, but then instead of stopping here, and I am mandated to stop here if my entropy function is truly extensive, and then but then it is not. Because it is not, I am allowed to, or I take the liberty of going one step further. So, if I have small deviations from extensivity, I have to go one step further, and I end up with this next term here. So, recall that the slope is, of course, continues to be the reciprocal of temperature. So, in order for S1 to reach a maximum, it is imperative that this S, the second derivative, be negative. So, we are going to assert that it is negative, and we are going to give a name to the second derivative of the entropy versus internal energy at the most probable value, and that is in terms of what is called the specific heat per particle. So, CV is, V stands for constant volume. So, we will get to that later, but right now it is just a name. So, it is a whole bunch of things. The important thing is there is a minus sign there, and of course, there is an implication that the second derivative of the entropy function with internal energy is its reciprocal is extensive. So, which is why I have pulled out N1, which is the number of particles. So, the implication is temperature, which is already intensive, and a lowercase c with a uppercase V means specific heat at constant volume per particle. So, that is the meaning of that, and because it is per particle, it is an intensive quantity. So, why do I have the right to claim that the reciprocal of this is extensive? Because if it is extensive and it is negative, I have the right to say something like this, otherwise no. So, what gives me the right to assume all this? Negative I already told you, because otherwise this will not go through a maximum, but extensive is easy to see, because after all what is S dash dash, I mean two derivatives, that means you take one derivative, this becomes intensive, and then you take one more derivative, which is so this is intensive quantity 1 by temperature, and then this is U in the denominator. So, it is 1 by extensive quantity. So, that is why I have written this as 1 by N1. So, now let us rewrite my the net way of doing things. So, what is this? I have given us new symbol to this. So, I do not want to confuse people. So, let me write down what this is. This is nothing but U minus U1 times omega of U1. So, that is what that is. So, I have just given it as a different name. So, notice that it is still a function of U1, because I am taking into account fluctuations. I have not replaced U1 by U1 star. So, the U1 is still available. So, if I choose to replace U1 by U1 star, I get back my old result, which is this. So, in other words, this product is nothing but the number of ways of rearranging the microstates of the reservoir times the exponential of minus beta times Helmholtz free energy. We did this already, but what is the new ingredient is this one, and this is because of fluctuations. So, I am now taking into account the possibility that the entropy function may not be fully extensive. So, as a result, I get a distribution of this sort, and of course, I have skipped some steps here, and I encourage you to go ahead and fill in some of those steps yourself, because it is very hard for it does not look nice for me to include all the steps in a presentation of this sort, and in any event you will be lost if you do not do it yourself. So, this subject I already told you several times that physics is not learned, it is not like watching a movie on your laptop screen, or it's actually taking a piece of paper and pen and working out, following along, working out the details as the instructor explains things to you. So, we end up with this expression which tells me that the overall ways of doing things where the internal energy is u1 is the most probable value times a fluctuation. So, now I can go ahead and add up all the u1s, and unlike the other time when I took the easy way out, instead of summing over all the u1s, I just chose to replace it by its most probable value. So, now I am going to do something less lazy, which is actually sum over all the u1s. But notice that I am doing a classical physics type of analysis. So, the energies are not discrete. So, in other words, summation here, summing over all u1 is the same as integrating over all u1s. So, even if u1s are positive, of course, I have at the back of my mind some kind of an ideal gas where its energy is mostly kinetic energy and it's positive, and well, as a result the lower limit is u1. But then I have the liberty of replacing the lower limit by minus infinity if I can convince myself that the contributions from u1 all the way from minus infinity to 0 can be neglected. So, it is like I have just added a whole bunch of zeros because I have included a new range. I have to strictly start from 0 and go to infinity, but by making this approximation, the claim is that you can go all the way from minus infinity to infinity, because minus infinity to 0 hardly contributes anything, and that is going to be the case only if I can convince myself that if what is the maximum value of this integrand in that region of u1 being minus infinity to 0. So, the maximum value is when u1 is actually 0. So, when it is anything bigger than 0, it is even well, it is not bigger than. So, notice that u1 is on the negative side. So, it is so you either have 0 or something slightly negative, or even more negative, even more negative. So, if u1 is very, very negative, notice that it is u1 minus u1 star. So, that is already a very negative, and very negative makes this highly suppressed. It is e raised to minus very negative squared. So, that is a large quantity and it gets suppressed. But however, the way to minimize this is to make u1 as less as possible from the negative side. So, in other words, make its magnitude as less as possible, which is basically make it approach 0. So, in other words, all I have to make sure is that even if u1 is 0, this is still negligible. So, if it is negligible when u1 is 0, it is certainly going to be negligible when u1 is more negative than 0. So, how do I convince myself that it is negligible when u1 is 0? You just have to realize that u1 is extensive and it is just a number of particles times some intensive quantity, so long as that is much larger than this quantity. So, in other words, I am just convincing myself that u1 is much larger than 2 t squared n cb. And that is certainly going to be the case because u1 is extensive, which is proportional to the number of particles, and the square of that is going to be huge compared to this quantity, which is proportional to the number of particles. So, the left hand side is proportional to the square of the number of particles, the right hand side is proportional to the number of particles. So that is certainly justified. So, given that it is justified, now we can also form a probabilistic interpretation of this expression that I just wrote down, and the probabilistic description is like this. So, suppose I ask myself, suppose I have a collection of system plus reservoir, suppose I have many copies of that. Okay. So, I have copies of a system plus reservoir, system plus reservoir, system plus reservoir. I have a huge number of copies. So, I randomly put my finger on one of those systems and I ask myself, what are the chances that the energy of that system is between u1 and u1 plus du1? So, the answer is that is of course going to be proportional to du1, because it's so I'm asking what are the chances that the energy of a system is between u1 and u1 plus du1 is certainly proportional to du1. But then it's also proportional to this quantity, because after all this is the number of ways in which you can rearrange the microstates of the system and of course the reservoir such that the system's energy is u1. So it's going to be proportional to this, because this is the number of ways in which you can do that. So, as a result, I am entitled to make this claim that the probability, so if you have this is called an ensemble, so this imaginary collection of system plus reservoir, so many Xerox copies of system plus reservoir, so these are mental copies that you make, and this is called an ensemble. So this ensemble, you can ask yourself what is the probability that in this ensemble the energy of the system is between u1 and du1. So it's like, so the answer is that you count how many systems fall in that window, that means with energy between u1 and u1 plus du1, and you divide by the total number of systems in your ensemble. So that is your number of systems which fall in that window, and that happens to be by definition p times du, and p is now the probability distribution of finding that system in that window. So now from this expression it's clear that I can write like this, and this is by construction properly normalized, because if I integrate over all u1 I get 1. So now I can go ahead and ask myself, so remember that when I started off I kind of totally ignored the fluctuations altogether, but that was conceptually wrong, because then if it's extensive it doesn't go through a maximum, so I don't have any right to replace a summation over its most probable value. So obviously that is only valid if it goes most probable value, and it goes through a most probable value because there are fluctuations. So it appears now that it's a worrying situation, because now it appears that I have to after all take into account fluctuation, because they appear to play such a central role. But then happily we are not in such a difficult situation, because we can go ahead and evaluate the precise magnitude of that fluctuation. So what we can do is estimate what is known as the root mean squared deviation of the energy of that system in that ensemble. So using this probability distribution. So when you do that, so you recall that the root mean squared is defined in this way. So you look at the deviation, you square it, and you take the mean. So this is taking the mean is basically averaging over the probability distribution, which is what I have done here. So when I do this, I end up with this result. But then notice this is the square of the deviation. So when I take the ratio, so now I look at the deviation and I look at the ratio of the deviation of the fluctuation of the internal energy, the estimate rather. So in that ensemble, and I look at the ratio of that fluctuation with the most probable energy, and that comes out to be inversely proportional to the size of the square root of the size of the system. So this is a very important result, central result in statistical mechanics, which says that that when the system sizes are large, that even though conceptually fluctuations are important in order to ensure that the number of ways in which you can rearrange the microstate actually goes through a maximum. So if you ignore fluctuations, it doesn't go through a maximum, it just keeps increasing. So conceptually it's important for fluctuations to be there, but fortunately the precise magnitude of the fluctuations are not that important. It's just the fact that they exist is important, because when you evaluate the fluctuations themselves, they come out to be heavily suppressed by the number of particles in your system. So that was mostly a classical description, but then I can go ahead and also repeat this activity for a quantum system. So recall that in a quantum system I had done something very similar to what I did earlier for a classicalish system, where I had energy, volume, where energy was continuous, that sort of thing. That's what we've been doing till now. But now for a quantum system, if you recall, there were these funny angles called theta and phi over which I had to integrate. And then I invoked something called a saddle point method, of course without proving it, but where I said that it's legitimate to replace this by some star, some quantities called theta star, phi star. These are the analogues of the most probable values that I was talking about till now. So, the quantum analogues of the most probable value. But here too, this makes no sense at all if this W doesn't have a feature which is known as a saddle point. So it so happens that it's only when this W goes through a saddle point, then you can do this. So I'm not going to go through the technical details. We can kind of postpone those details to a later date, or maybe you can look it up in any of the maths books. But from a physics point of view, all it means is that just like in the earlier few slides, I was compelled to take into account quadratic terms which correspond to fluctuations. Here too, that's all I do. The linear terms of course vanish identically, precisely because that is the definition that yields by setting the linear terms in the Taylor series to 0 yields the definitions of. So in other words, these are obtained by setting the linear terms to 0. So you have 0th term, then immediately I jump to the quadratic term. So the linear terms are 0, and which leads to these expressions. Okay. So this is how I'm going to stop. So if stop means stop the Taylor series. So I've stopped the Taylor series at the quadratic term. So let me evaluate these coefficients. So these coefficients are nothing but the second derivative of W with respect to theta and phi, and then there's the mixed derivative with theta and phi. So now W is defined in this fashion, and then if I go ahead and evaluate this, I get these nice expressions. So for W theta phi, what does this mean? This means take WQ and differentiate once with respect to phi, then again once with respect to theta, and then you put theta phi equals phi star and theta equals theta star. So that's what that means. So similarly here it means you differentiate with respect to phi twice, and you put phi equals phi star and theta equals theta star. So when you do all that, it's a little bit tedious, but it can be done. Notice if I differentiate twice, these things go away. So only this survives, and then I rearrange my terms. And what is Nj? So remember what Nj was. This is the average number of ways in which, the average number of bosons or fermions depending upon the value of Q that occupies energy level Ej. So Nj is the average number of quantum particles in energy level Ej, and that happens to have a mathematical expression of this sort. So that's what that is. So I'm just recollecting. So bottom line is that this W theta phi has this expression, W phi phi has this expression, and W theta theta has this expression. But what is common to all this? Of course, they are all very simple looking, but what is also common is the fact that they are intensive quantities, because recall that this is kind of the size of the system. So summing over all the j's effectively counts the number of energy levels, and each levels are populated by particles. So in some sense that becomes extensive. So it becomes scales with the size of the system. So that divided by n is basically an intensive quantity. So these coefficients here, they are intensive quantities. So we have to keep that in mind as we proceed. So now we go ahead and proceed, and we see that we can evaluate this integral, and we end up with this. So when you take into account fluctuations, the bottom line is the answer for the entropy including fluctuations is related to the answer for the entropy by ignoring fluctuation, which is why I have called it with a subscript ext and meaning extensive entropy. So, this is extensive entropy, and then there is a contribution due to fluctuations which leads to deviations from extensivity. If you take the log on both sides, you will see that it tells you the precise way in which entropy deviates from extensivity. So, of course, this is not at all important if n is huge. So, keep in mind that if n is of the order of 10 raised to 23, this is going to be proportional to 10 raised to 23. This is this is going to be proportional to 23 because it is a log of that. So, 10 raised to 23 is huge compared to 23. So, it makes no difference whether I subtract this or not. So, for huge systems, fluctuations just like conceptual role in the analysis, they do not play practical role. So, that is something to keep in mind. Okay, so I am going to stop here. In the next hour, I am going to tell you what is an important notion known as specific heat. So, we are going to study the specific heat of ideal gas, classical ideal gas, classical Fermi gas and classical Bose gas. All right, so hopefully you will join me for the next hour. Thank you.